All right, welcome to Next Gen Manufacturing Nexus. Today, we're diving deep into the absolutely incredible world of aerospace manufacturing. This isn't just about putting planes together. This is about defying gravity, conquering unbelievable forces, and really achieving the impossible with every single part. So, let's see how it's done. Just look at this. A modern jet engine it's just a masterpiece of power and complexity. Now, to build something like this, you can't just be good at your job. You have to operate right on the absolute edge of what materials and technology are even capable of. And when I say power, I really mean it. A single large jet engine turbine can crank out over 100,000 horsepower. To put that in perspective, that's more power than the entire starting grid of a Formula One race combined. And that kind of immense power demands an equally immense level of precision. So what does that precision actually look like? Well, we are talking about tolerances as tight as 1,000th of an inch. That is literally thinner than a single human hair. In the world of aerospace, that's not some ambitious goal. It's the bare minimum requirement. That's because the stakes are, well, they're astronomically high. This quote says everything. Inside an engine that's spinning at thousands of RPM, a single microscopic flaw in one tiny component can set off a catastrophic chain reaction. There is zero room for error. None. So this brings us to our first huge challenge. How on earth do you manufacture parts with that kind of impossible accuracy? Let's dive into the tech that actually makes it possible. Okay, so here's the core problem, right? You have to sculpt these components, like these super intricate turbine blades, from some of the strongest superalloys on the planet. I mean, these parts have to survive extreme temperatures and forces, all while holding their exact shape. And the solution? It's a technology that has completely redefined manufacturing: CNC machining. The best way to think of it is as a robotic sculptor. You have computer-controlled tools that just carve away at solid blocks of metal with mind-blowing accuracy, and they can create almost any shape you can dream up. This technology is what allows us to create critical parts that honestly were once thought impossible. We're talking 5-axis machines sculpting those complex turbine blades for peak efficiency. Other systems carve lightweight aluminum for the fuselage and craft the high-strength titanium landing gear that has to withstand incredible impact forces. It is truly the backbone of modern aerospace construction. But it's not all about metal, right? The other big challenge is this constant push for structures that are both unbelievably strong and ridiculously light. And that's where advanced composites come in. But here's the catch. Their strength comes from the precise, painstaking way their fibers are laid out. So the solution? Another huge leap in automation. Automated fiber placement, or AFP. And this stuff, it is absolutely revolutionary. You have robots precisely laying down thousands of individual composite fiber bundles, controlling the orientation of every single one. This lets engineers build strength exactly where it's needed, creating parts optimized for weight and performance in a way that manual methods could never, ever touch. Okay, so we've made our super precise parts. But how do we make sure they last for thousands of flight hours under constant, brutal stress? This brings us to the next challenge: forging unbreakable strength. The hidden enemy in any aircraft is something called metal fatigue. Think about it like this. You bend a paperclip back and forth. Each little bend seems harmless, right? But tiny, microscopic cracks are forming and growing until suddenly it just snaps. Now imagine that snap happening on a critical aircraft component. It's catastrophic. So how do you fight this invisible threat? With a surprisingly simple yet totally ingenious process called shot peening. You can think of it as a microscopic, high-speed hammer. Millions of tiny little particles are blasted at the metal's surface, not to remove material, but to create this powerful layer of compressive stress that basically acts like armor. And this comparison just illustrates the effect perfectly. Before peening, the surface is in tension. It's basically being pulled apart, which is like an open invitation for cracks to form. But after shot peening, bam! That surface is now in compression. It's being squeezed together. This compressive layer is like armor that actively slams the door shut on fatigue cracks, dramatically extending the life of the part. So, we've built our parts with incredible precision, and we've fortified them against fatigue. But are they actually perfect? Now comes maybe the most critical step of all, inspecting for flaws you literally cannot see. I mean, this is the ultimate quality control challenge. You have this brand new multi-million-dollar component in front of you. How in the world can you be 100% certain there isn't a tiny, deadly flaw buried deep inside it without, cutting it open to check? Well, the answer is a whole field of science called non-destructive testing, or NDT. Basically, think of it as medical imaging, but for machine parts. It's a whole collection of techniques that let inspectors see inside solid components and verify they're perfect. And it's not just one trick. There's a whole toolkit of NDT methods, each designed for a specific job. You've got ultrasonic testing. That's basically a medical ultrasound for metal, using sound waves to find internal flaws. Radiography is your classic X-ray, perfect for spotting hidden voids. Thermography uses infrared to find problems in composites. It's like seeing if the material has a fever. And eddy current testing uses magnetic fields to find tiny surface cracks invisible to the naked eye. Each one is a crucial tool in the hunt for these invisible threats. And on a real aircraft, these techniques are put to work every single day on the most critical areas. Ultrasonic and eddy current testing are absolutely essential for finding those fatigue cracks and any corrosion on the fuselage, the wings, and the skin panels, all the components that take the most stress up in the air. So all of these processes, the machining, the forming, the inspecting, they're all being totally revolutionized by one powerful force: automation. So let's look at the future, which is where intelligence meets machinery. And here's the key thing to understand. Automation isn't just about speed, it's about reliability. As this quote points out, putting robots on the job with these NDT tools drastically cuts down on the risk of human error, which makes the whole inspection process way more consistent and ultimately safer. And we can see that future taking shape right now. On the left, that's a fully automated robotic shot peening machine delivering a perfect, repeatable result every single time. And on the right, that's the next step, integrating AI-driven diagnostics with these robotic systems to create an inspection process that isn't just automated, it's intelligent. This is what the next generation of manufacturing looks like. We're talking about AI that can spot defect patterns a human inspector might miss, robotic systems that can crawl into hard-to-reach areas inside a wing or an engine, and real-time monitoring that could predict a failure before it even happens. It's a fully integrated, automated, and intelligent approach to quality and safety. And this all leaves us with one final, really fascinating question. As these manufacturing technologies get smarter, more integrated, and more automated, what fundamental part of an aircraft, the wing, the engine, the fuselage, is going to be completely reinvented next? The future flight is being built as we speak, and the possibilities, they're truly endless.